Hi everyone, today we'll talk about CAPSNET. My name is Karandeep Singh, and first we will discuss about the problem with CNN. So if you look at these two figures here, if we use CNN, we have to train this kind of images for it to detect at the runtime. So we have to give all kind of rotations as augmentation to the data set for the network to work. And the other drawback is if you look at this image, it will detect as a face, and also CNN will detect this as a face due to the pooling, and both the pictures are similar for the CNN. The output will be similar, the probability will be similar. So the problem lies with max pooling. Even Hinton, who is the godfather of deep learning, says the pooling operation used in CNN is a big mistake, and in fact, it works well is a disaster. That max pooling loses a lot of valuable information, and it does not encode relative spatial relationship between features. So we should use capsules instead, because they will encapsulate all the important information about the state of feature they are detecting in a form of factor. So vector. So I'll tell you how this capsule works. So if you look at this two tabular information, so we have a capsule here, and this is the traditional neuron where we multiply the weight and the input, and that's how, and then we give the nonlinear activation, and it's a scalar output which we get. But in the capsule we get the vector output, and we use a squashing function which makes the this vector in 0 to 1 range, and we take the input as a vector, and we give output as a vector. So that's how a capsule network work. And also what is a capsule? So a capsule is nothing but neurons. So these neurons capture color, width, angle, and height of a image. For example, if there is a person image here, and I take this pixel out, so this pixel, we will apply this capsule on this pixel, and we'll get color, width, angle, and height. So what output we will get as m is the 0 to 1 intensity, and the param is your color, width, angle, and height. So that's what you get. For example, if there is a person face on top right, so the output of this will be different from this bottom right person face, which is angled and tilted at some degrees. And the other important thing is dynamic routing algorithm. In a neural network, you have input, you have the output, and you have some weight, and these weights are trained in backprop. But in CAPSNet, we have C as well. So you multiply all these weights with C, and this C is dependent upon the data. And the routing algorithm works like this. So the first line of the routing algorithm tells what you have as input. L is the lower level layer, U is the output which we get, and R is the number of routing or iteration. And at the last line, you can see it's a vector output which we will get. So in the second line, you will see there's a coefficient Bij. So Bij is something which we have never seen in neural network. This is a coefficient which simply stores a temporal value that will be iteratively updated, and after the procedure is over, it will be stored in Cij. And the starting the value of Bij is 0. And if you see at the line 3, we will repeat these iteration 4 5 6 7 r times. And in the line 4, we are calculating the vector Cij using the softmax. And softmax, why softmax? Because it makes sure that each weight Cij is a non-negative number, and their sum equals to 1. And softmax enforces probabilistic nature of coefficient Cij. uh, okay. And in the next iteration, I mean, at the first iteration, the value of all the coefficient will be equal Cij, because on the line 2 Bij was set to 0, right? And next, in the next line, we'll calculate Sj. Sj is nothing but summation of Cij and uj, which we have uh, initially taken. And after that, we apply the squashing. So what we do is we use squashing non-linearity that makes sure that the direction of vector is preserved but its length is in 0 to 1. So if you see here a squashing formula, so here we are left side is converting into 0 and 1, and here we get the direction, so you applying it with unit vector. So that's what we do in uh, uh, and on the line 7 there we are doing the update function. So this is how the weight update happens. So this step capture the uh, main routing algorithm. It's much similar than how what we do in CNN weight update, but little change adding this squashing function. And now let's discuss about the bias. So the bias is, this is designed to parse the hierarchical structure of physical world and assumes that higher layers of hierarchy are made of entities in the lower layers. For example, if there is a face, so first we'll detect eye, and then nose, and then the lips, and this is passed from uh, a different layer, and then we aggregate that into lower layer. So this assumption is there, and the other is that we preserve the spatial hierarchy. For example, the person face should also always look like this, it should not look like this maybe. So that's the biasness, and the assumption is it's takes part to hold relationship as spatial relationship, and it achieves equivariance. So equivariance is the if input changes, the output changes in the same way, and it assumes that object can be decomposed into set of capsules. And if we talk about the relation with other ML approaches, so it works on the limitation of CNN. So it's a better CNN by capturing the spatial hierarchies, and it works on focusing on spatial relationship and pose information, and it's an extension of using the pooling layer and locality in CNN. Like pooling is used to decompose the high level feature into low level, but it also focuses on preserving the spatial relation. The hyperparameters are number of capsules and their dimension, and routing algorithm, how many times we have to iterate, learning rate, regularization, and neural network hyperparameters. The limitation is performance can be highly dependent on number of iteration, higher computational and memory requirement, and it's active research. So still people are, I mean, now in 2024 we have a lot of optimized version of CAPSNet, but earlier when it was launched, the idea in fact was there in Hilton mind since 2011, but Sarah and him, they completed this in 2017. So it took a lot of time for coding, and also because of the deep learning GPU constraint earlier which we had. Sample application is the object detection, where we have complex spatial relationship, and also in robotics, used in a lot of robotics, especially in lidars. They have started using this for mapping the environment from 3D world to 2D world as well. Sorry, from 2D world to 3D world, and also used in medical image analysis. So these are the references. Thank you. If you have any question, do tell me or email me. Thank you.